operating system. He is heavily involved with the FreeBSD project, core team member for many years, and as far as this topic is concerned, he's also one of the co-authors of the precision timekeeping protocol. So this should be great. Thanks.
All right, thank you, Sammy. So as Sammy said, I'm George Neal, and I'm here to talk to you about computers, clocks, and network time.
Time is an illusion. Lunchtime doubly so.
Yes, so as Ford points out, time is an illusion. So one of the interesting things about dealing with computer time and time generally is that really time is an illusion, and it's created by people, for people. We know it provides ordering of the day, necessary for basic human communication. Try to form a sentence or a thought in which you don't think about time.
Time is an illusion. Lunchtime doubly so.
So
time is an...
Stop that. There we go. So, you know, time has gotten narrower and narrower over time. Lots of time in the sentences. You know, we had seasons, then we get down to months, and we get down to days, we get down to hours, minutes, seconds. In computer-based time, we've mostly gotten this right, although there are some cases where we get it very wrong, which I won't talk about just yet, but maybe a little bit later. What we care about in computer-based time are, of course, the finer grains, seconds, milliseconds, microseconds, and nanoseconds, and how we handle those. So I want to talk about a few things today, and I apologize. I realize I'm going to vibrate as I talk because I normally walk when I give a talk, and I can't really walk away from the lectern. So if I swing back and forth, I apologize to the poor guy with the camera. So let's talk about a few things. What we're going to talk about a little bit is how we use time in our programs. But what I'm going to talk about for the most part is how we use time in deployed systems. So how many of you in this room write programs that only ever execute on one computer at this point? Right. None of you. So all of our deployed systems have multiple clocks in them, and getting those all to line up and figuring out when they line up and when they don't line up and what the impact of them not lining up or synchronizing is a lot about what this talk is about. Time, it turns out, is pervasive. Time is something we care about in almost everything that we're doing, and it's something that is, in particular, a room full of developers or programmers that we don't normally think about. We sort of expect that it's handled for us by the system. And sometimes it is, and sometimes it is not. But as you all just pointed out, most systems are distributed systems, so this whole question about what time is it really depends on where you are. So from the simplest perspective, almost everyone who's ever written any bit of code, no matter what language you write in, has at some point called get time of day, which I like to call the traditional interface. Most modern operating systems have a slightly better call than that, clock get time, for finer grain control. When you ask the system, what time is it, it doesn't give you a very accurate answer. In particular, how you ask the system the question will determine the accuracy and the length of time the answer takes to come back and how much it costs to ask the question. This is something that most people, when they first start dealing with time, don't realize, and so they will often use the most expensive version of get time of day to say, oh, well, I need to know how often my packets arrived. On every packet, timestamp it with get time of day. I can tell you that that is a recipe for disaster. So when we program with time, we have to actually really consider which APIs we use, because different APIs have different impacts. In particular, one of the things you don't want to do is ask the operating system kernel what time it is every time, because that's a very expensive operation. And that's an operation that also depends upon the underlying hardware. So we're going to talk a bit about hardware today. Depending on which motherboard your system is running on, it may have a better or worse quality of time source. And that may mean that the kernel may take longer or shorter amounts of time to get an accurate time from it. So there's only a couple of system calls to get this, which all then get mapped up into various high-level languages, but how you use them is really important. So when most people first come to this problem of dealing with time, especially in distributed systems, and here's my other question. I'm going to ask a lot of questions because I want to keep you awake until lunch. How many people are management? Excellent. Oh, okay, 3 of you. So here's how I got into time. Now, a lot of people get into working on time because they're really fascinated by clocks and timekeeping, and they're somewhere on a spectrum. I'm also really interested in time, and I'm somewhere on the spectrum, but I got into this not quite at gunpoint, because I was working for people who were building distributed systems to deal with high-frequency trading, and they said, how come our clocks aren't all accurate? We're running NTP, which is the network time protocol, and I'm like, I don't know, why aren't clocks accurate? And the problem is that people who've never really dealt deeply with computer-based timekeeping don't have, for want of a better word, an emotional connection to how bad it can be. So some of the problems with computer-based time. So when we work with computers, we get used to a certain level of accuracy. Sort of, if I add A and B and they don't equal C every time, then there's something wrong with the hardware I've bought, and I throw out the hardware and I buy new hardware. If I have a server and its clock wanders, I don't throw out that server, although I have considered it. And why is this? Well, it turns out that in that $1,000 or $2,000 or $5,000 box that you bought, the price of the crystal that is used to keep time is 10 cents. So it's really cheap. And in terms of computer-based crystals and timekeeping, you get what you paid for. So I have gone to major board manufacturers with the backing of a financial institution with serious cash and said, can you build me a motherboard with a better crystal? And they said, no, not really, we're not that interested. So if you're going to buy server class hardware, you're going to get cheap crystals, and time is going to wander if you don't do something about it. Systems run hot and cold. So if you look at time graphs of your servers sitting in a data center somewhere, and for instance, again, you're a financial trading company, you will notice that between the beginning of trading and the end of trading, whenever that is, your clock runs at one speed, and on the hours when you're not doing that, it runs at a different speed. Crystals age. So someone somewhere in a mine cut a piece of quartz, and that was cut down to a very small wafer. And that piece of quartz was put into this crystal, put on a motherboard 3 years ago. The ability of that piece of quartz to vibrate at the same rate that it was vibrating when it was first put in that board changes over those years. And that will change, again, everything about time in the system, right? So remember that crystal is the thing that determines the rate and the speed at which everything else in the system runs. The bus, the board, the CPU, everything, and what time it is. Workload effects. So if you have a very busy system, then your clock may run faster because you're keeping all your cores hot, and that's keeping other things going at a faster rate, or it can have a negative impact. All this comes down to being harder than you or your management might think, right? So people who don't spend a lot of time dealing with time and computers, they come down and they're sort of like, why aren't these all the same? And you're like, well, there was this guy named Einstein. And then there's this paper by Lamport in '78. And let me show you this proof. And then they walk away and they're like, just fix it. So you spend the rest of your life, or in my case, the last 7 years, just fixing it in various ways. So I'd like to show you two clocks. This is an iPhone. That's a crap picture of an iPhone that I pulled off the internet. If I were to turn off all of the networking features on that phone, including its LTE radio and its Wi-Fi, it would be equally as accurate as the watch on the right, which is my Japan Rail 1966 engineer's watch, and that's a wind-up. And after some number of days, they would probably wander about the same, because a cheap crystal is basically no better than a mechanical watch built in 1966, which is sort of depressing. And I'm probably not going to put a mechanical watch in my server, but they're relatively similar. And I can't give a talk without stealing something from XKCD. So I know we're all going to put fancy Apple watches on our wrists eventually, and some people are wearing Pebbles and all this stuff. Technology always makes things better. We had regular watches, then we had phones, and now we're going to put smart watches on our wrists, which will only be accurate if they're on the network.
Time is an illusion.
Lunchtime doubly so.
So what happens if I disconnect all of my machines from an external source of time? This is a log graph of the local time on a laptop plugged into a really good clock. So one of the cool things about having worked on the precision time protocol for the last several years is a couple years back I asked one of the major clock makers if I could buy cheaply a clock from them, because the good clocks are expensive. And they said, what's your address? and they sent me to my Brooklyn apartment a really nice clock with GPS, and I live in a building that's old enough that I can see 9 satellites out my window. So the source of this time is extremely good. The destination of this time is a laptop with some problems, as you can see. So how bad is this? Well, that graph starts out at 0, 0. And then I just ran things for 2 hours, and I didn't adjust the clock at all. I just recorded what time I thought it was compared to what time the clock thought it was. And after 2 hours, I was already 15 milliseconds behind. This is typical behavior. This is a 2 or 3 year old laptop. It's okay. It's not a server machine, but I can tell you that the crystals are pretty much the same and have about the same quality. So, who cares about all this stuff? I mean, it's 3 o'clock in Peoria. Who cares? Well, so there's a bunch of places where we really care about this. Debugging distributed systems. Now, you all admitted that you work on distributed systems. One of the things that makes debugging a distributed system really difficult is answering my mother's question. So when my brother and I would get into a fight as kids, my mom's first question was, who did what to whom and when? Right? And she didn't know that she was teaching me distributed systems when I was 8. But it turns out that it's a really good lesson for debugging distributed systems, because that's pretty much what you want to know the moment something breaks. So what was the source, what was the destination, and who did what to whom and when? When did this happen? Well, if you can't line these things up, then you can't make any sense of what's going on in your distributed system or your data center. It's really difficult. Reconciling online transactions, if you can go to Amazon and say, hey, I didn't buy that because you can show something wrong in their system, then you probably get your money back, and they would be really annoyed. Robots and automation. Turns out that a robot arm moving at 40 kilometers an hour, if you get the timing wrong, will smack the guy operating the thing next to it, and then you'll have a lawsuit. That's very bad. Power grids. So in the United States, power is at 60 hertz. If you want to bring up a bunch of power generating stations and synchronize them into the grid, they need to be synchronized to each other within a 60th of a second. Because if this, I don't have a good graph of that, but if this doesn't overlap correctly, very bad things happen. Spectacularly bad things. I mean, they look really cool when they explode, but very, very bad things happen. So power grids need to be within at least a 60th of a second, 50th if you're in a country with 50 hertz. Cell networks. So for those of you who are using LTE, when next set of LTE features that come out will require that base stations in sort of one area, spanning about 2 kilometers, need to be synchronized to each other within 1,100 nanoseconds, 1.1 mics. That's really, really hard. But if you want to do things like watch YouTube on a high-speed train, which I guess people want to do, then that's going to be important. There's also a lot of other stuff. There's some voice canceling. There's some other features that are pretty important to LTE Advanced. And they have really tight time constraints. So
Time is an illusion.
Lunchtime doubly set.
So why did I do that to poor Ford Prefect? So when we talk about time, there's a couple of terms that I really want to get people to understand. Synchronization versus synchronization. So most people are familiar with synchronization. That's the idea that my clock and your clock and the other person's clock are all showing the same time at the same time. You wind up having to get into bits of Einstein to know when at the same time is, but let's ignore that because it's painful and it's math. But that's synchronization. It's like our clocks are all lined up. It's 3 o'clock, it's 3:01, it's 3:02. Synchronization is something most people rarely think about. And synchronization is a second really 1 second long, right? And so in a system in which the crystal can vary how fast the frequency is going based on heat and load and the age of the crystal, then your synchronization can change. And so a second might not actually be a second. It might be faster, it might be slower, and that's what happened to poor Ford's voice, is the synchronization was changing over time. Generally, you can fix this, or fix is a strong word. You can get better quality, which is what time protocols and timekeeping is all about, by doing a few things. You can put a pulse per second input into a system which, at the top of every second puts out a very narrow pulse. There's some very nice, expensive machinery to do this. You can do this at other frequencies. Some people will run a 10 megahertz signal into a board to try and get, that second to be exactly 1 second. So it all comes down to your tolerance, right? So in terms of accurate timekeeping, the way it was first posed to me when I started working on this stuff, I talked to, it's funny, Paul Henning's name comes up a lot, PHK Malik, that was Paul Henning Camp. The other thing Paul Henning works on a lot is time. He's done a lot of work with NTP. He's doing some more work with NTP now. When I first started looking at these problems, he was, I'd known him a long time, and I thought, okay, I'll ask Paul Henning what he thinks. And I said, well, I need to get more accurate time on these servers. And he said, well, how much are you willing to pay? Because that's actually one of the definitions of what your tolerance is. You can always get a more accurate time source, and you can always build a more accurate time system, but it generally costs an order of magnitude more money per accuracy level. And so the question that you wind up having to come up with is, well, what is your tolerance? So we're in New York, so there's enough people who know what high frequency trading is, and that there's this place called Wall Street where they do that, which actually they don't do it there. They do it in Hoboken and Weehawken and other places. But because of the speed of financial transactions using electronic trading, there are now regulations about how good your clock has to be. Now, the regulations are currently laughable, and actually when I started they were really, really laughable. FINRA, who regulates a whole bunch of the financial industry in the United States, says your computer's clock must be within 1 second of the time defined by NIST, which is the National Institutes of Standards and Technology, whatever it is. If you can't get your clocks to be within a second of anything, then really you should be doing something else. And certainly not trading stocks, and definitely not trying to keep time. But that's very likely to change. Now that most financial institutions are measuring their transaction round trip times in mics, if trading firm A and trading firm B both enter trade on NASDAQ or NYSE or something, you need to know probably in under a second who showed up there first, because that's going to define who wins, who made the trade. So the financial folks care a lot about this, and people in high frequency trading have always cared because they care for their own data quality, but the financial regulators are going to get into this as well. So what's your tolerance? Oh, mentioned the robot arm thing. If your robot arm is moving at 40 kilometers an hour, however fast it's moving, if you whacks the guy next to the robot, that's bad. Power lines, cellular networks. So it's always application dependent, right? So in the case of LTE advanced features, we're talking about 1100 nanos between stations. In the case of power lines, 50th or 60th of a second, or probably 1/2 that. The robot arm depends on the robot. And whatever your application is. So when people are doing any kind of high frequency work on a machine, on a group of machines, the question is, what's the fidelity between them, right? How much do I need to know? So, how have we solved this problem? And this isn't well, there is no final solution to this problem, but there have been approximations over time. So I mentioned better crystals, not on commodity hardware. You're very unlikely to get it. There are some people who will sell you some very nice add-on cards. They cost around $1,000 a card. So if your data center has 500 machines in it, you can give them $500,000 and wire up your data center for GPS to every single machine, and then your clocks will be a lot more accurate. They won't be perfect, by the way, which I keep having to point out. You will not, there's no perfect time here. They'll be better. But they're expensive for large deployments. The state of the art, of course, has always been what network time protocols have done, and this is the ask a better clock. So what does that mean? Well, we posit that a clock with a better crystal exists. So yes, a 10-cent crystal isn't very good. And we can't get that on our motherboard. But we know people who make better crystals. So there are oven-controlled crystal oscillators, temperature-controlled crystal oscillators. There are rubidium clocks. There are cesium clocks. There are all kinds of crazy esoteric clocks that you can get. And these have better frequency stability so that synchronization problem isn't there, right? Or that synchronization problem is reduced. So a second really is a second. And then your clients, which don't have good clocks, ask the better clock, hey, what time is it? And then they set their own clocks based on what time it is. It's as if I stood here all the time asking all of you, hey, what time is it now? And you all sort of chimed back and told me what time it was. There are complications with this particular scheme. So when we talk about the better clock in terms of stratum, what's a stratum 0 clock? Well, that's a clock that has a certain quality, and stratum 1 would be a clock that's following a stratum 0, and stratum 2 follows stratum 1. And so if you look at an NTP, the output of NTP on your laptop, if you've got a Mac laptop, you're running an NTP. I suspect Windows are doing the same thing. Linux is doing that, FreeBSD. It'll tell you what the stratum of the upstream clocks are. I'm talking to a clock that's of this quality. You ask what time it is, and then you do this game called time transfer. So, it's not instantaneous. I, as a time client, will ask the server, what time is it? But that message took some time to get there, and it took some time to get back. And that time is often asynchronous, not asynchronous. That time is often not constant. There's jitter. And so then what the local clock does is it measures and attempts to correct for this network propagation time. I know that I asked you what time it was 3 milliseconds ago or 10 milliseconds ago because I know the network delay, at least I think I do, and then I steer the local clock. So one of the other things that most programmers never deal with, but those of us who deal with kernels do, is there is a way to steer the kernel's clock based on external input. And what I mean by steer is, we get an input saying, oh, you're behind, to go faster. And so what we do is we crank up the speed a little bit and we try to catch up. And then it's like, oh, but you're going too fast. And you go back down. And it's like you've got this one throttle and you go backwards and forwards. And this is what results if you ever look at the graphs of time and these oscillations, because you're never going to lock to one and be stuck there. It's just not going to happen. So that's the whole theory. That's how this works. But let's see what goes wrong. So the gold standard in internet timekeeping, NTP, originally, it's been around for a long time. You can see how long it takes us to standardize a new time protocol. A long time, nearly 20 years. This is what's used by internet-based timekeeping. If you've got time set on your laptops or your servers, you're doing this. This is a client-server model. Your default polling time is once per 64 seconds. So that means it can take hours to synchronize with another clock because you're not asking that often. Now you can reduce the polling period, but you can't reduce it that far. You can reduce it down to a few seconds. And if you're polling across the internet, it's just going to take a long time to synchronize. So I mentioned synchronization, synthesization. Let's talk about network jitter, right? So we all know that if you set up a data center with one switch and a bunch of hosts, that there will be no jitter in the packet transfer time between hosts. Networks never lie, and they never drop packets, and they never induce packet latency. Oh wait, no, all of those things happen. So network jitter is extremely important in terms of figuring out the quality of the time you're receiving at a server. Because if you can't work out the network jitter, you're not going to be able to remove that noise from the signal, and you're not going to be able to adjust your clock correctly. So a lot of what I'm going to talk about are the sources of jitter and how to get rid of them in your systems. And then I'll keep talking about grandmasters. A grandmaster is not a chess player in this presentation. The grandmaster is the clock that you're synchronizing to. That's the better clock. So how many of you deploy stuff in Amazon and in the cloud generally? Wow, you all have your own servers. That's awesome. There's one Kate in the back has stuff in Amazon. This is a graph of what happens when you install the network time protocol by default in a virtual machine sitting in the cloud. So that's a little hard to read. I'll tell you what this is. Those swings are plus or minus 5 milliseconds. That's an entire day's worth of data. You can see that this is with the default NTP config. I don't have a laser, so I will not move my mouse. Notice that the peaks aren't even regular, right? Like at some point earlier in the day, something happened where it swung wildly, and then for some hours in the middle of the day, it didn't swing very much, and then it started to swing wildly again. Maybe that's a periodic thing that happens every day. Maybe they move the machines around in the cloud once a day, or they pull statistics once a day, or they do something once a day, or who knows. But anything that they do is going to cause the time on all of those cloud instances to move, and to move, plus or minus 5 milliseconds. Maybe you don't care, but you probably do. So, I talked a lot about NTP. Let's talk about some improvements on the network time protocols. So back in 2002, the IEEE and some people who knew a great deal about math and not a lot about networking developed a time protocol called the Precision Time Protocol. And so for those of you who've ever looked at network protocols and you've got a lot of free time and have insomnia, go look at version 1 of this protocol because it is incredibly bad. I have never seen such an odd way of encoding data in a network packet before or since. And so that didn't last very long. It also turns out, and I had not known this having dealt mostly with IETF protocols, in the IEEE, you have to re-up your protocol every 5 years. So every 5 years there's a call and there's a committee and there's a lot of phone calls and there's a lot of committee meetings, a lot. And you have to revalidate each protocol. So that process started sometime after IEEE 1588 version 1. Version 2 came out. Clearly they had asked some people who knew about networks how they might encode their bytes correctly. And so version 2 of the protocol is the protocol that we currently have. And this is used by a lot of folks and a lot of the motivating applications I talked about earlier. So IEEE 1588 has been used more recently in the financial area, but before that, factory floor automation and power systems and cellular and phone networks. Those are the 3 big consumers of that protocol. And then the finance people, sometime around 07 or 08, kind of the time I entered that industry, said, "Oh, there's a protocol for this. We can maybe improve stuff." IEEE is currently in the process of creating version 3 of the protocol, which I have been involved in some of the email discussions, mostly as a watcher, because I don't have an infinite amount of time in which to talk about how many angels should dance on the head of a pin. It's a very interesting process watching how these things are made. It's like watching sausage being made. But there will be a version 3 of the protocol. And it'll have some interesting features. We'll see how it goes. So some very interesting things about PTP, one of which is it was designed purely for a single segment LAN. Now, I don't know how many people own a very large single segment LAN, but that was their original plan. And it uses multicast. So I'll ask another question. How many people think they understand how multicast works? Wow, okay. All 5 of you are wrong. And if you're right, I would love for you to go work for a major switch or router vendor because the people there really don't understand how multicast works. I can tell you that every time I have turned on multicast on a piece of equipment, either end host or switch or router, it has broken every single time. I now have bugs open with every major switch or router vendor, either by me or by people I've worked with, because, it's like, well, we didn't take that case into account. Great. But PTP uses multicast, and for a very good reason, which I'll talk about. So what's really cool with PTP, and I'll show you why this is possible, is we can get inter-host accuracy synchronization under a mic using software only. There are a bunch of people who've released hardware support for this on network interface cards, and I'll explain why you would do that. And that will increase your accuracy, but it's not completely necessary. We've been able to get pretty low just with software and some very carefully managed networks. So this is a fun graph. I'll explain what this means on the next slide, but what you should note, if you can't see it, you should be able to see it on the slide, is that's plus or minus 5 mics, 50 mics, sorry. But let me talk about this. So that's another 24-hour graph. This is, same laptop you saw wandering all over the place, listening to the same clock, but actually, managing its clock correctly. Why do you see so many dots? Well, there are hundreds of measurements per hour. The median in the middle of that big graph is 300 nanoseconds either side of 0. Most of that data is between plus or minus 30 mics, and the numbers are at the 50. That client is pure software, and the master is this really nice Meinberg M600 that I got from the Meinberg folks. So the reason this works is not because the protocol is more brilliant than NTP or any sort of special magic. Although I do wish there were magic for time protocols. If I could kill a chicken to improve the quality of my time, there would be a lot more dead chickens in my apartment. But that doesn't work. I tried that. It's really messy. The reason it works is there's hundreds of measurements per hour. So I talked about the polling interval for NTP, right? You can get that down to like 16 seconds. We are checking the time and checking our time versus the grandmaster every second, right? And we are checking the round trip time between ourselves and the grandmaster within a few seconds all the time, all day, every day. Which means instead of having very large swings when we realize we're slow or fast, we have these nice little swings where we're like, just a little faster, just a little slower. Don't move that too hard. It's not magic. It's just, oh, well, we're willing to spend more network bandwidth to do this. If you're building a network, an internet scale time protocol, you probably don't want every host on the internet asking perhaps a smaller number of servers every second, what time is it? Because then you won't be able to watch YouTube because all the data will be time data. I think that would be cool. Netflix, YouTube, not so much. They don't agree with me. So how does this work? So this is a multicast protocol. And so what happens is we've got 4 packets we use. Sync and follow-up. And what sync and follow-up are really responsible for doing is the time transfer part of the protocol. I talked about how you do time transfer. So the sync and the follow-up have the time that the packet left the grandmaster at the top. And then all the slaves, and there can be many more than these, see those packets at the same time. They're multicast. So everyone sees the same packet relatively at the same time. There's some propagation delay. And this explains why, when they specified the protocol, they said single segment LAN. Because if these packets pass through a switch, well, okay, you've got a cut through switch. Maybe that's not so bad. But if they hit a router and they sit in a router queue for any amount of time, then you really don't have a good way of figuring out how much time that packet took to get to you. And then there's 2 more packets after the sync and the follow-up. The slaves then have to determine, well, how far is the grandmaster from me, across the network? And so they send this delay request, which they randomly space out so that all the delay requests don't collide on the grandmaster at once, because that would be really bad. And then the grandmaster sends this delay response. And they do this all day, delay request, delay response, and then these syncs and these follow-ups come out. And so this is a different model than you get with NTP, where your clients are saying, what time is it? What time is it? What time is it? It's more, oh, I know what time it is, or at least I know what time you think it is. And occasionally, or frequently, I'm going to say, how long does it take for me to get a packet round trip between us? What's the latency? So I talked a lot about jitter and how bad jitter is. So what are sources of jitter? Well, routers are pretty much the worst, because routers have queues that can be unbounded, that are bounded, but they can be very big in terms of how long it takes a packet to transit a queue. The variance can be in milliseconds. Switches are a little better. Certainly, cut-through switches, what I try to specify when people use this stuff. Lengthier link. You have different link lengths, and for those people who've done sort of the crazy high-frequency trading stuff, we know about, everyone's got to be equal. So I've got this 5-kilometer bit of fiber that I've put between myself and NASDAQ because me and the other person have to be also 5 kilometers away because light happens to travel about this far in a nanosecond. So links, electronic noise, and then software. So one of the biggest sources of jitter probably after routers is the software. And why is that? So there's a whole bunch of things that can happen on a system that you never need to worry about unless you really care about latency and jitter. If all you care about is bandwidth, you don't care about things like network interface card interrupts. So modern NIC, you've got 10 gigs coming into a box. How do we do that? Well, one of the ways we do that is we batch packets, and we do that by preventing the card from interrupting us too often. If there's a lot of traffic, we're like, well, don't interrupt us. We'll just take these packets in batches of thousands instead of just one at a time. That's great if you're transferring a ton of TCP. It's really, really bad if you're dealing with time. So one of the first bugs that I found when we were doing this on 1 gig networks, there was this weird 8 kilohertz signal. You could see the signal right in there. It's right at 8 kilohertz. I'm like, what is going on here? Oh, interrupt moderation is on, right? So the NIC's interrupt moderation was at 8 kilohertz, and you could just see the signal. It was destroying the time signal. So NIC interrupts can be a problem. Packet buffering, OS scheduling, right? So if the OS is in particular, the time daemons, they don't do very much, right? I mean, 1 packet a second is a really low level of packets for most modern pieces of software. So, the OS is going to think it's idle, and it's going to take all of its stuff and it's going to move it away. And then a packet's going to arrive, and it's going to be like, oh, I needed all of that, and it's going to try and get it. So OS scheduling, and then the software stack itself actually induces a whole bunch of jitter into the measurements. So All right, I'm going to talk without the mic for a second. I'm going to make the poor camera guy follow me. So when I sorry, you need to move on. So when we first started doing this stuff, if you looked at the way that we got time, we did it the most expensive way and in the worst place possible. Right? We did it at the very top of the software stack after the packet had passed through the entire operating system and the sockets layer, and had been, sitting in queues and going all these places. This is terrible. Right? This is a really poor way to get time. And so then over time, you look and you're like, well, I don't want to have to write a NIC driver just to make time better because that's difficult, and I'll really try to avoid that. So eventually we're like, the next thing you say is, well, it turns out the IP stack can give us bin time. So that avoids all the jitter involved in being past that UDP and passed through a socket buffer. Great. And then next thing we looked at was, oh, well, it turns out, at least on FreeBSD, and I think on Linux, I did this on FreeBSD, I can tell the packet capture system, which sees packets before any other part of the network stack, take the time right here and take it really accurate. So one of the other problems with bin time and get time of day is so bad on this. Bin time gives you mics. This time gives you nanos, and it gives you a relatively good nanosecond. Not down to the nanosecond, but better than microsecond timestamp. And then finally, you've got hardware timestamps, which some systems have implemented. In particular, if you, a lot of people in financial use SolarFlare 10 gig NICs specifically for this. But I will tell you something amusing. SolarFlare, you know who wrote their precision time protocol daemon? Turns out they used the open source one, which they didn't happen to tell us initially until I looked at their logging output for another customer, and I was like, those logs look really familiar. Let me send some email. Oh, okay. You're welcome. And thank you for using our software. So the next thing that you find is that people do a NIC timestamp. And so, for instance, these expensive clocks like the Meinberg and Symmetricom, and now they're Microsemi, and other companies, what they're doing to get really accurate time with really low jitter is they've put special hardware in that at the physical, just above the physical layer, as the bits come off the wire, they can timestamp right there. Intel NICs have this, SolarFlare, Chelseo sort of, but basically there's a lot of the support in there. And now there's timestamping support specifically for the precision time protocol. So if the NIC sees a PTP packet, it knows what the bit pattern is, and it's like, oh, I should put a really accurate timestamp in that. There's a slight problem with this. So if you want to, that's great if you want to get a really accurate time on the NIC. But if you want really accurate time in your system, you still got to transfer the time from the NIC into the operating system and into the motherboard itself. So you still got a time transfer problem. But again, over time we're getting better. We're going to get to 0. So these are all the places in the software stack the time can go. So now for my next trick. So one of the things I mentioned was multicast. And this is something that I added only to the R version of PTPD. There's a couple of open source PTPDs, but this one's very widely used. So I looked at the protocol, and after my eyes stopped bleeding, I realized that there was something kind of interesting. There's a sequence number. Now, anyone who designs a network protocol without a sequence number should be hanged, at least. I think the other things I can't put on tape. So great, we've got a sequence number. All packets are multicast. All hosts see packets at the same time. Well, that's very, very interesting. Because now we've got a way on every host, independent of talking to the clock, or because we're getting packets from the clock, of trying to line the hosts up against each other. Now, most time protocol people don't really think about this, because what they really care about is sort of a small number of hosts. Like, I just want to make sure that my host and the grandmaster are close. Like, my stratum 1 is close to my stratum 0, my 2 is close to my stratum 1. But for those of us who care about widely distributed time in a data center where you've got hundreds of machines, yes, I care that they're close, but probably at some point, someone's going to ask the question, well, just how close were they at time t? So we can tell you that, unfortunately, and this may be the one thing I ask for in IEEE 1588 v3 over v2, the sequence number is 16 bits. And at once a second, that's not a full day. All right? So that's kind of unfortunate, because then it means you have to play tricks of knowing when the day started, and it just means that I've got to write more Python code or R code to go and reconcile the data. I don't want to do that. I want it to be free. So give me 16 more bits. So this is what I call quality files. This is something we've only got in PTPD. And what we do is every time a sync packet comes from the grandmaster, we just record the system's time. Like we record the time that the server thought it was with that sequence number in a file. And then we can post-process these files and show the offset between hosts. And this is a really powerful thing if you're deploying this in a data center, right? It's not as important if you've got 3 cell towers that need to be synchronized. Maybe they care, maybe they don't. But if you've just recorded a day's worth of equities or some other, a day's worth of some data, and you really care about how different things line up on different hosts, you kind of care about this. So this is one of the things we added. So I talked a lot about PTPD. This is a BSD licensed open source version. It originally supported IEEE 1588 v1, and then thankfully that went away. So we went to v2, and the code got a lot cleaner. It'll actually interoperate with NTPD. It can talk to the NTPD if it needs to. Currently it's on SourceForge. It will eventually be on GitHub. Once our next release goes out, we're going to move to GitHub because it's what all the cool kids are doing now. All right, so my last slide is not the question slide. My last slide is a joke slide. And this is a joke only people who deal with time care about. So let's talk about the leap second. How many people know what a leap second is? Excellent. How many people know when the next leap second is? Well, you do now because you've got the slide. Leap seconds are the bane of any timekeeper's existence, right? So this is to adjust between, what astronomers think time is and what the rest of us think time is and all this other silliness. What it really is it's an extra second unless you're pulling it back, and we've never had a leap second that goes backwards. We've only had leap seconds go forwards. We've only made them longer. But we add a second to the clock, and I originally thought, because all the leap seconds I've ever dealt with, and who puts that on their resume? All the leap seconds I've ever dealt with have been December 31st, which is kind of nice because, well, most people are drinking heavily on December 31st, and very few people are doing important things like trading stocks or flying airplanes. So on June 30th this year, the leap second will occur at the Greenwich Mean at UTC at midnight. When will it occur in Tokyo? I recommend nobody fly to Haneda or Narita on June 30th because it'll probably be fine, but you never know because all the clocks are going to move at something like 3 o'clock in the afternoon when all the air traffic is coming into Asia. So I recommend Asia trips, 29th, July 1st, not so much on the 30th. So leap seconds are the bane of our existence because there are a couple of reasons they're a problem. One is most people have never dealt with them. They don't happen very often. And in particular, my favorite leap second, and again, who has a favorite leap second, was the one that I think was around 2000, I think it was 2008, because the clockmaker that my employer had bought their clocks from also didn't know about leap seconds, which means that all of the grandmasters were wrong, and then all of the machines everywhere that synchronized to them were off by a second. And I can tell you that this made people very upset, and we switched who our clockmaker was right after that, because I was never going to use that clock again. So leap seconds are just this thing that if you're dealing with distributed time, you have to deal with whenever there's a person who sends, honest to God, there's a telegram, right? This is sent by telegram initially to all of the observatories around the world that there will be a leap second June 30th, 2015, or December 31st, whenever it is, or any other month. And then everyone else scrambles and goes and checks their software to make sure that it handles the leap second correctly. So I'm going to leave my gag slide up, and I'll write down when the next date is. Any questions? Or have I lulled you all to sleep before lunch? If you have questions, there's a mic here that I have to give to someone. Yes?
Do you not care to comment on the power company and the frequency they run and how accurate that clock is if you run the old days? Yeah, the question is, the power companies run a frequency that's sort of accurate at plus or minus 15 seconds, maybe better these days. You can't care to comment on power company clock keeping?
So I actually, thank God, have never been responsible for power company clock keeping because I'd much rather destroy financial markets than have explosions. It's just me. I know that's sort of crazy. I am pretty sure at this point that all of the power companies, at least in the US, are using something along the lines of PTP. They're one of the reasons that it came into existence. I mean, they always had to have this accurate timekeeping because, for instance, when they brought the Northeast back up after the last big power outage, I mean, that's basically why you don't turn them all on at once, right? So I don't think they're running the same clocks they ran back when, that was the most accurate. They're pretty much running something. The only way you can get as big a distributed power system to do that is to be well within that 60th of a second. I'm sure it's way lower than that. Wait for the mic.
Thanks, George. You talked a little bit about jitter. Can you talk a little bit about asymmetry and how
Sure.
you deal with that?
So the question is about jitter versus asymmetry. So all of the time protocols, all the NTP and PTP both do the same thing for asynchrony, which is they're taking the number and they're dividing it by 2. So that's not great. Asymmetry can still introduce noise, although often what it will do is it'll introduce a fixed amount of noise. And that, at least in the PTP case, can be tuned. It's one of the configuration options. So if you're like us, or like the stuff I've worked on where you've got, people who've got their own data center and it's all under their control, right? This isn't going to be true if you've got like multi-tenant systems. But if you've got everything under your control and you know that you've got some asymmetry, you can actually tune the daemon for that and say, oh, I know that it takes longer to go one way than the other. And that'll be taken into account in the calculation. But the normal way to do it is to just take the 2 and have it. Yep. There.
So you mentioned the cloud systems. How well would PTP work in a cloud system? Or it seems like the NTP is the only option, right? If you put your systems in a cloud.
So there are, I am told, though I have not worked with, I am told that there are cloud providers who target people like finance. So they've built clouds that are sort of more dedicated towards that, and they will provide better timekeeping. The biggest problem in the cloud isn't so much, well, yes, NTP would be a problem. You could tune that down. The bigger problem that we have, in particular in virtual machines, which I didn't go into at all really in this talk, is that getting time out of virtual machines and having that be accurate has been one of the things that has plagued all of the virtual machine providers. So VMware does a little better than everybody else because they have enough people who host on it. But if you're using something like QEMU or VirtualBox or any of the other sort of virtualization technologies, you're generally the getting the time accurate out of that is something that was basically thought of completely last. It's just one of those things that people started doing the cloud stuff and they didn't think about time-sensitive applications because their thought was, who in their right mind would run their time-sensitive application in a virtual machine? But then, people were like, well, we're just going to throw this up in the cloud and see how it goes. And we'll see how it goes. So I know that I've heard that there are cloud providers who will provide better time service and who care about this. I don't believe that the big providers like an Amazon are one of them.
So does PTP in its current form provide any security around, rogue clients sending out sync messages?
Let me restate the question. You asked about security and PTP, right? Okay, because NTP and security, you can just Google for that and have a good laugh, because that's been the laugh of 2014. When it was designed, it was fine, and then we let all these people use the internet, and that was a mistake, right? Like, it was way better when just the NSF could use it. Anyway, so in terms of the precision time protocol, PTP v2 has 0 security, nothing. There is nothing in there to, in particular, one of the common misconfigurations is to have 2 grandmasters accidentally both be on the same, network. Because if you artificially set, you can set the priority of your grandmaster. You can say, oh, I've got a failover. But if you set them the same, they'll both keep talking. And then your clients will be like, you, no, and then that's very bad. So there's no protection against that. There are discussions in IEEE for the version 3 talking about security. But the real problem is that if you're talking about like keying or hashing or any of this stuff, those are expensive operations. Those introduce jitter into the time protocol. So you've got the time purists on one side who are like, absolutely not. If you can't control your network, don't use this, and then there are other words they use that I won't use in a public presentation. And then you have sort of the people who are like, well, yeah, but we run a network with multiple tenants and we'd like to, So we will see what happens in the standardization process in terms of security. Right now, my feeling, and I'm not a time purist, I'm just a guy who has to deal with clocks. My feeling is that there are so many variables inherent in getting time better or close to right that trying to introduce the security thing, if you really care about like this sub-microsecond stuff, you're never going to use it. You're going to, I could be wrong. In 5 years, like it's this thing in the cloud, right? Who would ever run time-sensitive stuff in the cloud? So I'm going to say here that in 5 years, someone could come down and go, oh yeah, you didn't think that we would ever like do this, but we will. So my feeling is, if you really care about sub-mic, high-quality time, then you're the kind of person who has picked your servers, picked your network gear, picked your links, picked your switches, and has designed it from end to end. Because I've seen people do it the other way, where they're like, let's take a lot of cash and throw it in the air and see what falls down, and those systems are not under a mic. Those systems are over a mic. So the security question remains to be seen. I haven't seen any proposals from the IEEE committee that make me think that it'll be practicable for very high quality time, but again, I could be wrong. Anyone else? All right, thanks very much.